before we start the table method, we need to recall this very important property of the inverse Laplace transform. So if you want to find the inverse Laplace transform of something like alpha fs times beta gs, so alpha and beta are constants. So what happens is you can actually break this down to two of them. So you can write this one like this. So you can write this one as the first alpha times the inverse of the first term, and then beta times the inverse of the second term, because this is the most important property when we use the table method, because you can just split them into multiple parts and then we use the table to find one by one. So that means the next line you can write this one as simply alpha fs is the original function, and then for the next one gt is the original function. So you get the inverse, so you can split like this and you can find the two functions. This is the most important property. So let's see how we can use this in the table method now. In the table method, what we do is we match the functions given with the table, and then we try to get the answers using the formulas available there. And you can find the link in the description for the table method, and you can, that's the table that we're going to use, and that's the table like you need to remember. So try to remember as much as you can. It can help you in an exam. Just you can recall those very quickly. So let's start the first one. So we have the inverse of 1 over s minus 3 over s squared. So the first what we can do is we can actually use the linearity, and we can write this like this. So we can say the first one just the L inverse 1 over s, the first one, and the second one actually you can pull the negative 3 out because that's like constant, and then we can write this one as L inverse 1 over s squared. And then what we can do, we can recall these two formulas from the table. We know that the Laplace transform 1 is 1 over s, and also Laplace transform t is 1 over s squared. So because of that, when you go backward or when you go the inverse, now you can write the answer. So the first one is going to be 1 because of 1 over s, and minus 3, and then 1 over s squared is t. So that means it is t. So that's the answer. So you can have 1 minus 3t is the answer for the first one. So let's look at the next one. So now we have as the second one L inverse 1 over s plus 3 plus s over s squared plus 9. So by the linearity we can write it like this first. So we have these two expressions. Now what we can do, we're going to match these two with the table that we have. So we can recall these two first. So we have the first one, what we normally call the eat function. So it's a Laplace transform for e to the at is 1 over s minus a. Remember the minus sign, that's minus sign, opposite sign, that's how we remember. It's opposite sign, a and minus a. And then the cosine omega t is s over s squared plus omega squared. Here there's a plus sign, it's very important. And for the sine, you can see it is omega over s squared plus omega squared. So same denominator, both are same denominator. First one is s, second one is omega. So now we can see we're going to match with that, and in the first one you can see so the first one is the eat function. Here we have a negative a, we have a positive 3. So positive 3 means actually you can look at this like this. So you can say, because since you negative sign, you can rewrite this one as s minus minus 3. So you can do that, because then it's going to tell you what is the actually the a value. So you can see in this case a is negative 3 when you write it like that. You write with the negative sign. So that's the idea. And the next one is clear. So we have the same thing. So next one what we can do, we can add s over s squared plus 9 you can write as 3 squared, because you have to write with the square. So that means in this case omega equal to 3. So that's omega, so which is equal to 3 now. Okay, so now we can use the table, so we can write the answer now. So use the eat function. In this case a is negative 3, so it's going to be e to the negative 3t, that's the first term. If you do the second one, you can see it's s over s squared plus omega squared, that is the cosine one, because that's a s term. It's the cosine one, so that means it's going to be cosine omega in this case is 3, so it is 3t. So that is the answer for the second one. So you can see how we go. So we can split them into two first, and then we match with the table, and we try to figure out what is the a value and what is the omega value, and then we just plug in that to the formulas. So let's look at the next one. So we have this interesting one. Inverse of 1 plus 1 over s plus 1 over s squared plus 1 over s cubed. As before, we can split them into 4 parts first. So we have these 4 pieces. Now we go one by one. Actually, now you can see that there are two new things that we need from the previous ones. So let's look at let's recall these two. So we have the so-called Dirac delta function here. So when you have the Dirac delta function, it is the e to the minus as. That's what you get, e to the minus as. And when you plug in a equals 0, you get this one. When you plug a equals 0, it's a Dirac delta t equal 1. So that's what we need for our problem, is a 1. And then we also have t to the n. If you have t to the n, what is going to be a factorial n divided by s, n plus 1. We add 1. And then this is true for n going from 0, 1, 2, 3. N equals 0 is the 1. And n equal 1 is t. We already have those two in the previous one. So now it's you can generalize it. What is the factorial n? Factorial n means you start with n and then you multiply n minus 1 like that until you get the 1. So we get 3, 2, 1. So just multiply all the way up to 1. That is factorial n means. So factorial 3 means 3 times 2 times 1 like that. Okay, so let's use that here now. So you can see in the first one we can actually plug in the value. So it is inverse of 1, that is delta t. So that part is done. And then 1 over s, we already know it is 1 from the previous example. 1 over s squared, we know that is also t. And then the next one is 1 over s3, s to the cube. But we can see that it doesn't really match with this one, because what you want to do is we're going to rewrite this one as 1 over s to the 2 plus 1. That's how we do, because you need a plus 1 here. But when you write 2 plus 1, you also need the factorial of 2. Factorial 2 means 2. So what we normally do is we write a 2 inside and then we write a 2 outside. So what we do, we multiply by 2 and divide by 2. So we do that. So because of that argument, you can write this one as 1 half, and then we can write this one as L inverse. So I'm going to write the steps here. So it is 2 over S 2 plus 1. So we write this extra step first. And then we can write the final answer like this. So it is delta t, and then 1, and then t, and then we have here 1 half t to the, in this case n equal 2, you can see n equal 2 now. So since n equal 2, so you get t squared as the answer. So that's the final answer for that one. So yeah, try to redo this one and understand what's going on here. Okay, let's look at the next one. As the next one, we have L inverse 7s plus 2 over s squared plus 3. And you can see that this doesn't actually match with any of the formula that we have on the table. So what are you going to do? We actually use another technique that we normally call the splitting technique. So we're going to split them into two fractions first. So we can write it like that. So we write these two after splitting into two. So this is a major step we do. And then what we do, we use a linearity, and use the linearity we can pull this 7 out of the fraction. And also we try to see what we really need. So that's a 2 term there. It is not exactly 2 we need, because you need this 3 means you can write 3 as square root 3 squared. So that means the actual term that we need in the top is square root 3 for the same one also. But here for this first one, you really don't need that t term, the square root 3 term here, because there is a s1. But for the second one, we actually need the term. So what we do, we're going to pull 2 out and we're going to put the square root 3 in. So let's see it. So we can write this extra step now. So we can write it like this. First, we're going to pull 7 out, L inverse, and then we can write this one as S over S squared plus 3. So that's the first one. For the second one, what we do, we pull this 2 out first, and then L inverse. So we have S squared plus square root 3 squared, so which is square root 3 squared. So what we need in the numerator is square root 3. So you multiply by square root 3 and at the same time divide by square root 3. So we do that. We multiply and divide by the same term. And then now we can see they're all gonna match with the table. So from the table, now you can write like this. So you can say it is 7. It's a cosine, so it's a cosine square root 3t. That's the first one. Why square root 3? Because you write 3 as square root 3 squared. So that's where the square root 3 comes. And for the second one, you can see you can pull 2 over square root 3. That's a fraction. And from the table, we can see you're going to get sine square root 3t. So that is the answer for the for this one. So what we did, we split them into 2 and then we try to match the term in the numerator. So we multiply and divide so that they cancel out each other, and we pull 2 out first, and then you can see they nicely match with the table, and then you write the expression from the table. So let's look at the next. So we do 2 more from the table. So as the next one, we have 3s over s plus 2 squared minus 7. So there are a few issues here. There's a minus sign. That's the first thing. We see a minus sign there. And also, you see that there's a 3 plus s plus 2 term there. S plus 2 term. So that doesn't match with any of the ones that we did earlier. So what will happen here is, we're going to recall this formula. This is like what we normally call the first shifting property. So let's recall this formula first. So we have this result. This is what we call the first shifting property. So what we have is, we have a e to the minus at term multiplied with another function ft. So if you have e to the minus at term, then what happens is actually you take the Laplace transform of the original function first, and then you replace s by s plus a. So that's the idea. You replace s by s plus a. So that's exactly what happened in this problem. You can see that this is actually going to match with one of the formula that we have in the table. So you see that these two formulas with the negative sign. So the first one is what we know, what we call the hyperbolic cosine function. There's h for hyperbolic. So what happened? Only difference is with the regular sine cosine, the negative sign. There's a negative sign. That's the only difference. Otherwise, it's like very similar to the sine cosine function. So these are for the hyperbolic function. Shin and cos. The first one is called the cos omega t. The second one is called the shin omega t. So only difference is the negative sign. So you can see now it's matched. So when you get a problem like that, what we're trying to do is we try to match with this. So you can see we forget about this plus 2 term. When you want to match, when you want to figure out what is the actual term, we forget about the plus 2 term. So you simply consider this one as s squared. So this is like s squared minus 7. That means it is very close to the cos function. It's very close to the cos function. But you also need a s plus 2 term in the numerator. We do not have that. That means we're going to recreate that term. So this is the like algebra trick we use for that. So we're going to add a 2 and subtract 2. But before that, we pull the 3 out. So we do this algebra now. So we write this one as we have a 3. So you can either pull out 3 or we can leave the 3 in. So let's say you leave the 3 in. So you write 3. Instead of s, you write s plus 2. Why is plus 2? That is what is in the denominator. So we write the whatever the term that you have. But when you write s plus 2, you are actually introducing a 6 to the new 6 there, 3 times 2. So what we're going to do is we can subtract that 6. So we can write minus 6. Now you can see it's matched with what we had earlier, and then divided by the same term, s plus 2 squared minus 7. Now what we're going to do, as before, we're going to split them into 2. So we can write it like this now. So we pull 3 out of the first term, and for the second term, what we're going to do, you can see that the 7 means square root 7 squared. So that means we need that term in the numerator. So what we do, we pull 6 out and put the square root 7 in. So we write it like this now. So we multiply and divide by square root 7. So we can multiply by square root 7 and divide by square root 7 so that they cancel. Now you can see we can use the first shifting property. So first what we discuss, what we do is we can know we just forget about this plus 2 term. Plus 2 term we can forget about. So we just consider this one as s over s squared type of situation. S over s squared. That means it is the hyperbolic cosine. Only thing that we need to do just to compensate the s plus 2 term, you need to multiply by a e to the minus a2 e to the minus at term. So that's the only thing that we need to compensate the shifting part. So that means your answer, you can write it like this now. So it is going to be 3. For the shifting part, we can write e to the, in this case, a equal negative 2, so it is negative 2t, that's the compensate part. And then what you're going to do for the other one is you can see it is the cos, and 7 means square root 7 squared, so it is square root 7 squared. Because of that, you're going to get square root 7t. That's the first one. And second one is similar, negative 6 over square root 7. And then the shifting part, that's going to introduce e to the minus 2t, is always opposite sign, so plus, here minus. And then this is shin, so this shin, you can see square root 7t. So that is the answer. So we use like several properties and some algebra tricks also. So we rewrite them first, introducing the term in the denominator, this plus 2 term that is in the denominator. So you rewrite the same one in the numerators. That's like a major step. And then when you do that, there's a problem because you can introduce a 6th term. Just to subtract that, you subtract, because you get a negative positive 6, so you subtract negative 6. And then after we do that, we split them and take out all the unnecessary terms and then leave the terms that is in, and then we use the table to get the final answer. So this is what you get. So let's do one more problem from a different type. So as the next one, we have 3 plus e to the minus 2s over s plus 4. So you can see that there's a slight difference in that. We have this extra e term there. So we didn't have a term like that in any of the previous examples. So that means this is like a different type. So what we do for this one is actually we have to use what they call the second shifting property. It says that Laplace transform of ft minus a. You can see that there's a t minus a and the ut minus a. What is the u function? U function is the unitary function. That's also like interesting property. So what it says that, so we have this u function, so u t minus a, so which is a piecewise function, which is equal to 1 if t is greater than or equal to a, and it is 0 for all the other values. So if it is 0 for all the other values, so that means if you look at the graph, it looks like this. So that means at a, it going to jumps to 1 and it stays at 1. So that's why it's a unitary. So we use the word u for that. So at 1, at a it is 1, and everywhere else it is 0. So, and then also it has a really nice Laplace transform. So the Laplace transform of that one is this. So it is the u t minus a, u t minus a is equals to e to the minus as over s. So you can see that you can get this one from this result if you plug in ft equal 1. So if you say ft equal 1, this is what you get. So it's like a result from the second shifting property. Okay, so now so what we can do, we can use the same idea here. So we can first split them into two first. So these are the two terms that we get, and then you can see the first one is actually is just the eat function. So in this case, a equals to negative 4. So because of that, you can write the first one is simply 3 e to the negative 4t. So that's the first one. The second one, we can use the second shifting property, and you can see again, this is the fs one. So fs is s plus 4. So what is the second shifting property says? So you can go to the actual function, you can find the actual function, in this case e to the negative 4t, the same thing, you get e to the negative 4t, but you want to replace that t by t minus a, you can replace t by t minus a, and also you need to multiply by the extra u term. So that means second one is going to give you, so you're going to go e negative 4, you're going to replace t by t minus a, so in this case t minus 2, because you can see in the expression the minus a match whatever the term, you put it there, and then you also need to multiply by the extra t minus 2 term. So that's what coming from the second shifting property, you have always need to multiply by the extra term. So that's what happened. So that is how you get the answer for this one. And so this is like one way to write it, and you can also write this one as like a piecewise function, because you can see there are two different cases here. So if you want to do that, you can see if t is smaller, you only get the first term, so e to the 3e to the negative 4t. So that's what happened when t is less than 2. If t is greater than 2, you get both terms. So you can write it like that, and you can see e to the negative 4t is common. So if you pull that out, you can write this one as 3 plus e to the 8. You get a e to the 8 when you multiply these two terms. And then, so that's a common, so we're going to pull it out, and then you get the common term, it is e to the negative 4t. So this happens when t is greater than or equal to. So that's how you use the second shifting property, and both of these are answer okay. So if you want to, you can write either of them, but the second one will be useful if you want to graph the answer for the second one. Okay, this is how you use the uh, table method to find the inverse Laplace transforms. Now try these 6 problems as practice problems, and you can comment below if you know the answer, or if you want to discuss any of these problems. So then, yeah, so you can make the discussion there. Thank you.